Welcome to panel 4. This is the predictability panel, and this has a nice balance of industry and researchers. My name is Tim Juliano. I am one of the moderators for this session, and my other moderator here is...
Yeah, hi, I'm Christine Wiedinmyer. I'm the Associate Director for Science of CIRES, which is a cooperative institute for research in environmental sciences at CU-Boulder. Hi.
Great. Yeah, and just to briefly go over the goals and outcomes of this particular panel, we just heard a lot about the observations, which are really critical for us to make good predictions, right? So in this panel, we'll be talking about predictions of fire weather, emissions, smoke, as well as wildfire behavior. And of course, we're interested in many different temporal scales. So this can range from event scales to seasonal scales. And really, we want to be able to identify kind of where we're at and what some of the main targets are moving forward, especially, of course, as it comes to industry needs and really how we can tailor, a lot of our methods and modeling. So to start, we're going to have Jordan Ambrogi from Core Electric Cooperative.
Thank you. Thanks everybody for having me. Happy to be here. I am the Wildfire Mitigation Program Manager for Core Electric Cooperative. Started as Core's utility forester. I am a certified arborist and utility specialist, as well as a certified wildfire mitigation specialist. This is Core's territory, split into our 4 operating districts. So as you can see, we operate from pretty far east out to Deer Trail in the grassy plains through the Parker Southern Denver metro area and Sedalia up into the foothills, incorporating the Rampart Range area, a big chunk of the Pike National Forest, and Park Valley to the west. From the north to south portion of the Rampart Range is one of the highest fire risk areas in the state. So wildfire mitigation is top of mind for us. We have close to 180,000 meters serving over 350,000 members, and total land area of our territory is 5,000 square miles. Some of our environmental risk drivers are the vegetation that we have, particularly through that Rampart Range area and Jefferson County specifically. We have many dense lodgepole pine stands, which are subject to high mortality. So it's both a fire risk as well as reliability. We also have a lot of aspen down in our Woodland Park district, which are prone to failure. And the failure of a tree into a power line, unsurprisingly, is a pretty big ignition risk for us. The terrain itself can vary quite a bit. We have the grassy plains out east, but we also have very steep slopes with loose granite soil, decomposed granite in much of our district, a lot of valleys, a lot of chutes and draws and stuff. So fire can really have unpredictable behavior across our territory and in various terrain. We are prone to drought, obviously. We have some areas where winds get channeled to very high speeds based on the topography, as well as a lot of lightning strikes. And in Jefferson County in particular, the density of the population within the wildland-urban interface poses one of the greatest risks we feel in terms of wildfire in our territory. Risk drivers from our system would be contact from objects such as trees, animals, vehicles, particularly construction equipment running into our power lines, equipment failure and contamination, and equipment contact, either wire to wire, construction, as I said, or during the course of maintenance. The business risk from a wildfire encroaching on our territory is, or our right-of-way and our transmission corridors in particular, are loss of service, internet and communications, and potential de-energization of our lines and impedance to restoration. Obviously, you can't go and restore or repair your facilities when an active fire is going. And even after the fact, you have to patrol every inch of that line to make sure that it is safe to re-energize and repair anything to allow you to do so as well. So the key focus areas for our wildfire mitigation program are situational awareness and risk forecasting, our inspection programs and maintenance, system hardening, and vegetation management. And some of the applications in which we use satellites, on the lower left here, you'll see this is a screen grab from a company called Overstory, which processes satellite imagery with AI to detect vegetation encroachment on the power line corridors, as well as tree health and identifying of hazard trees, measuring tree height relative to our lines so they can predict to some degree trees that have the potential to impact our power line. And one of the most useful products is they can deliver, using near infrared, a kind of heat map of tree decline in given areas, so we know where to direct patrols more frequently based on that level of tree decline. And on the right, that's kind of, it's more of the situational awareness piece. That's a platform called FireGuard, may have been mentioned earlier today by Intera. They use satellite imagery and thermal detection to identify fire starts. It's one of the first reporting mechanisms we have of fire starts in our territory. And they also provide all the incident aerial missions on an active fire, provide us with a pretty precise boundary as well. So we know how that fire is progressing relative to our system. And in addition to all this, the risk forecasting is a big component of our program as well. To determine where we focus system hardening and system improvement, as well as our inspection and maintenance programs. Thank you.
We get clapping in our session. Okay. Okay, next up we have Ronnie Abolafia-Rosenzweig. I had to ask him how to pronounce his name because I don't think I would have gotten that first try. So, slideshow. Okay.
Thank you. Hello, everyone. I'm a project scientist here at NCAR, and I'll be presenting on some of our fire and drought forecasting methodologies and frameworks with a focus on the Western United States. So before going into the methodologies, I'd like to touch on a historical context. So last year, Park Williams and others published a paper looking at the rapid intensification of the mega drought for the southwestern portion of North America, which covers most of the Western United States. So looking over here, this figure is from his paper. The red line shows the cumulative drought over the recent 22 years that we've been experiencing, which has exceeded any other mega droughts of a 22-year period in a paleo record going back to the year 800. So we're in this very historically significant time period. And then the blue line represents what the drought severity would look like if there was not anthropogenic climate change. So a great deal of this drought severity we're experiencing was attributed to climate change. Now, what that means is this yellow line is just from natural variability from 1571 to 1592. So if we superimpose climate change on top of this natural variability potential, we could be in some future experiencing very, very severe drought conditions, even more than the current mega drought. So considering we're in this historical mega drought and we've been practicing fire suppression, we're starting to see studies find that we're also breaking paleo records compared to fire. So Philip Higuera and others published that Rocky. Oh, wonderful. Okay, great. Thank you. All right, so Philip Higuera and others published finding that now we're looking at lake sediments that go back 2,000 years, and we're experiencing a historical context in terms of fire as well, which is what you would almost expect after over 100 years of suppression, as well as an unprecedented megadrought. So in our analysis of looking at relationships between climate and fire for potential predictability, we focused on the snow-reliant area of the Western US, which are the white shaded areas in the map here. We were particularly interested in the potential relationships between snow, drought, and fire, and quantifying these during the key drought months, which are June, July, August, and September, where 94% of the burned area occurred during our 1984 to 2020 period, covering the Landsat satellite record at the time of the study. So how did we quantify the relationship between climate and fire? We used a simple machine learning model. So a machine learning model is unique in that generally with a model, you give it an input, it gives you an output. In the machine learning case, you give it an input and an output, and then the output is actually the relationship between the two. So calculating the burn area as a function of climate, and then we evaluate how well this function performs on data outside of the training of the model. And so, oops, there we go. So using winter and spring summer climate, we were able to explain a large portion of the summer burn area variability with a high correlation between the climate-based function with actually the Landsat observed satellite burned area from 1984 through 2020. And this is just indicating that essentially there's this strong relationship between flammability and burn area across the broad scale Western United States in terms of both the interannual variability and the trend. But for predictability, we wanted to remove summer as a variable and understand how much of that peak fire season burn area can only be explained if we're only telling the model about what the winter and spring climate conditions are. And we found that around half of the interannual variability and half of the trend can be explained, which indicates that on the S2S or subseasonal to seasonal timescales, this pre-summer hydroclimate information can provide a large deal of the predictability for the coming fire season hazard. So on a broad scale, it's really interesting, but not particularly useful to managers. So then we move towards high resolution drought forecasting, looking at a 4-kilometer spatial resolution, using a similar statistical model. And so on the top here is an example of the output of that. So on the top are the actual monitored conditions for a few significant drought summers of 2007, 2011, 2012, and 2014. For meteorological drought on the top and agricultural drought on the bottom. And then below are an example of the maps from the 1-month lead time prediction outside of the training. So overall, this is showing that at a 1-month lead time, we're able to closely predict these maps of the actually monitored severity. And we found that this was a similar case for up to a 3-month lead time. Additionally, we were also finding that these models were able to accurately predict the cumulative drought area and not just the spatial distribution of the drought severity, with a high correlation between the predicted drought area and the monitored drought area from the statistical framework. I'll skip past this for time, but this is just showing essentially that our 3-month lead time forecast was able to capture a lot of these drought evolution characteristics between the time of prediction when the drought maps looked like this to the summer drought conditions that looked like this, and the predicted drought map looks a lot more like the summer conditions that we were trying to predict than the drought conditions at the time the prediction was made. So I'm gonna make a plug here for some really great research done by a high school student at Fairview High School right by here that I've been mentoring for the past year. He saw the Marshall Fire and was really motivated to get into the fire prediction world. Reached out to me, and we've been working on a project for the past year or so. And so we've all seen signs like this that give us some qualitative estimate of what the fire risk is. He was interested, can we make that more quantitative? Can we predict the probability of fire on a given day, a fire ignition given the meteorological conditions? So using a random forest machine learning model he created, he found that actually the model was able to discriminate between the probability of fire on days where a large fire ignited versus days with no fire occurrence across winter, spring, summer, and fall. So overall, that work that he did ended up winning him the Earth Science Division at the recent Colorado State Science Fair, so very proud of him, and really cool to see a young scientist getting into the field. So that's all from me. Thank you.
Great, thank you, Ronnie. Next up, we have Eric James from NOAA. And I think Eric will be speaking without any slides.
Yes, that is correct. Sorry, I don't have any slides. I'm Eric James. So I work at the NOAA Global Systems Lab, which is just down the hill here. And I'm going to be talking about our group's efforts to do numerical weather prediction with increasing focus on fire weather and smoke forecasting. So our focus is on numerical weather prediction for the next basically 2 days. So the kind of the short range forecast. Our focus is on rapidly updating models. So we initialize a new simulation every hour to bring in the latest weather observations, which enables us to take advantage of satellite information, data from surface stations, commercial aircraft observations, so that we can get the best starting point for our weather forecasts. And over recent years, we've been incorporating more and more complexity in incorporating different Earth system components into our modeling system, and that includes smoke in the last few years. So back in, so the system I'm talking about is the 3-kilometer high-resolution rapid refresh. It was mentioned by Joe in his talk in the last session, but it's a convection-allowing 3-kilometer grid spacing model over the conterminous US, and it's been operational since 2014. But starting around 2016, 2017, we started working to incorporate a very simple smoke forecasting component into the model. So that finally became operational in 2020. Some background about the model, we're users of the satellite data. So we have to use satellite detections of fires to initialize the locations of the fires in our model. So the operational HER uses fire radiative power from the polar orbiting satellites from the VIIRS and MODIS instruments in particular. And then we parameterize the plume rise for the smoke transport, as well as the amount of biomass burning emission. And we have just a single smoke tracer. These are operational models, so we have very strict computational cost requirements. And so we can't add a lot of complexity, so we just have a single tracer for the smoke. So once we have the smoke in the atmosphere, we can parameterize the plume rise, and then the smoke can be dispersed through the forecast. I think Joe showed an animation in a corner of one of his slides. I should have had a nice animation for you, but sorry about that. Essentially, then we can represent wet and dry removal of the smoke through the forecast, and we have boundary conditions of smoke coming from a North America scale model called the Rapid Refresh, which is 13-kilometer grid spacing. A key capability that we have is the interaction of the smoke with the radiation. So the HER can represent this direct feedback of the radiation and the smoke. So there's been a number of cases in the last few years, even here in Colorado, where there's been very intense shading of the ground by intense smoke plumes that have led to some really stark temperature gradients over short distances. And we can actually model that. We can actually predict that with our modeling system. So right now we're working on a next generation system that is going to replace the HER in a couple of years. And it's called the Rapid Refresh Forecasting System. It's 3-kilometer grid spacing, but it actually will have a much larger domain covering all of North America. So we'll be able to explicitly represent fires over Canada and Mexico, for example. And there's actually going to be 3 tracers in this model. There'll be a smoke tracer like in the HER, but also 2 dust tracers, so we can represent dust storms as well. So the goal is to have that in operations by 2025. And just one of the last things I want to mention. So obviously this is smoke prediction capability is really important, but we also have, we're also trying to represent the atmosphere as a whole. So we want to be able to predict all kinds of high impact weather, like high winds, heavy precipitation, And so it was mentioned in one of the morning sessions about the need for predicting high winds that could lead to fire ignitions. And we're actually able to do that quite well for certain types of windstorms. So the Marshall Fire situation a couple of years ago, we were able to predict, more than 12 hours in advance, the onset of this really intense windstorm here in the Front Range area. We have a paper actually that was just accepted in Weather and Forecasting describing our forecasts of that event and looking in more detail at that. Also, the recent Maui event, we're actually running an experimental domain of the HRRR over Hawaii, and we were able to capture the strong winds in that case too. So that's another use for our forecast. So I guess I'll stop there and look forward to the discussion. Thanks.
Thank you, Eric. Next up, we have Jackie Shuman. Jackie's working double duty today, 2 panels in a row.
Yeah, I probably should have passed this off. So before I went to NASA, I worked here at NCAR doing vegetation modeling. I also do not have slides, so we're in the same boat. And so I was doing dynamic vegetation modeling at the Earth system scale, working with here at NCAR with FATES. So FATES is the functionally assembled terrestrial ecosystem simulator. So essentially, within a lot of Earth system models, you have like a blob of vegetation, multiple blobs of vegetation that do not interact. So they don't look like a realistic landform. You do not have grasses and trees mixing together. A model such as FATES is an ecosystem demography model. And so you have vegetation of different sizes, and those different types of vegetation interact. And so you can have different patches, like the size of this room, and they would be time sense disturbance. And so for a very young patch, everything would be very short and tiny. And then for a very old patch, you might have some tall trees, you might have some short trees. And so my primary responsibility was developing the model for to include more explicit and accurate simulation of fire behavior and effects. And so within the fire portion of the model, a fire could come through, and depending on the energy of that fire, you would kill off all the trees, or you could kill off some of your tiny trees. And then the vegetation patches would have memory. And so then your fire behavior would be different at your next time step. So when you're working at the Earth system scale, you're talking about things happen daily, but for predictive capacity, you're really thinking out annually to decades. And so, so can we capture dynamic vegetation through time at that scale? Yes, we can. And the fire behavior responds to that. And so working within fire, we all know that there's a feedback between the type of fuels that you have on the ground and the speed of that fire, the propensity, whether or not that area is going to have more fire. And so those feedbacks are sort of self-reinforcing. If you have grasses, those grass areas tend to have faster fires that happen more frequently. And this is something that the model can capture. And so this is good news because we can use Earth system scale models to talk about informed policy. We're still working on getting FATES into the main, I say we, the community is working on getting FATES into sort of general operation, sort of as the standard version of the model. But it's an active area of research across a lot of global modeling centers. And so right now it's applied regionally. I was working in the tropics. There are a couple of projects in California that are using FATES. And then there are other types of models such as this within the community. And I'm going to pass it along. I don't know who's.
Thank you, Jackie. And last we have Lilly Jones, who I guess wears 2 hats, CIRES and Southern California Edison, SCE. And I believe you have slides somewhere here. Okay. Hidden back here. Oops. Okay, take it away.
I am working on a postdoctoral project at CIRES at CU-Boulder, and this is our team. It's a little bit unusual for a postdoctoral research project in that it's sponsored by an industry partner, Southern California Edison. Southern California Edison's motivation to sponsor this project was, I'm sure we're all familiar with what happened with PG&E. It's been called the first climate change related bankruptcy, but probably not the last. And SCE is strongly motivated to not become the next. So they approached CIRES to work on this project. I think we all know all this. I'm not gonna read through all this, but one of their primary goals is to develop a 3-month predictive model based on the vegetation life cycle to determine how vegetation could be impacting their power lines and their infrastructure. And so they want to take a proactive approach. I know some people in the last session were talking about how do we go from reacting to wildfires to predicting them. And that's really a non-trivial problem, particularly when you need real-time or short-term predictive capability. It's a lot different to take that approach than taking the approach of long-term predictability. There's different sets of tools that we have to use. And this project too is we have constraints from the science and engineering perspective. We also have constraints based on our industry partners' constraints, for their infrastructure and the resources that they have available and so forth. And so the 3-month time span was not a science decision. That is based on the resources that SCE has available to go out into the field. Their service area is about 2/3 of Southern California, and they have teams that go out and cut back vegetation from their power lines and so forth. So yeah, that's it for me.
Thank you, Lily. So that concludes the initial talks. So I'll invite the panelists to come up now and we can field some audience questions.
Are there any initial questions right now? Otherwise, I had a list going, but I'll let Brad go first.
So this is to Jackie. If I can understand, so right now that DEM vegetation model, it's working at the regional scale and you're trying to take it to global or the other way around?
That's correct. And so it's working at the regional scale, and then it's been run at the global scale.
Okay.
But we tend to initialize it with existing vegetation and then you move it forward. And so some of the benefits I wouldn't run it from bare ground at the global scale and expect it to give us an answer that looks like what we have today. And so there's a bit of a disconnect in terms of, how do you handle increasing carbon dioxide, carbon dioxide fertilization, dynamic disturbance. So there are a lot of impacts that aren't captured just yet.
Could you use it just for and I don't know the right terminology, but there's like 10-hour fuels and 24-hour fuels and that kind of thing?
Yes. And so it does have different fuel classes. And that's one of the nice things about the model. And so there are finer scale models that are used in the community, but at this Earth system scale, what we've implemented, it uses the same, very similar algorithms to what is in like WRF S-Fire. And so it has, and then I developed a crown fire component before I left, and a colleague is going to wrap that up. But it has different classes of hourly fuels, and so different sizes of fuels that then change through time with different moisture conditions. And this is, the fuels are populated based on the types of vegetation that you have. That portion of it still needs validation. And so right now it can capture across the tropics, you can get a distribution of trees and grasses based on climate conditions that looks reasonable compared to reality. And then the fuels also look somewhat reasonable, but it needs more attention. And so that's working on the fuels would be an area of focus at that scale.
Thanks. Hey, everybody, it's me again. So as a researcher, I'm leaning in a different direction, but I won't propose that part first for the question. Which one is more important from an industry perspective when it comes to, should we predict the thing first, or should we be able to just react when it's time to react, right? So like, do we really need to know when the fire is going to happen, or do we just need to know if a fire happens in this area, this is what we should do? That's kind of the question.
Assuming that's for me. For the utility industry, it's not so much about predicting where a specific fire would occur or not. I mean, that'd be great, but I don't think that that's necessarily realistic. But having accurate predictions of conditions that drastically increase the likelihood of, for me, equipment failure, tree failure near our power lines, and fire spread, those are the things that I need to know pretty definitively, because the decision we have to make is, are we going to preemptively de-energize our power lines? That's a very unpopular decision to have to make, and it's also a massive lift in terms of you have to patrol that entire line before you re-energize it. So those are the things, rather than the specific fire, those are the types of things that I need to know with as much certainty as possible.
And just to follow on that, what are the timescales? I mean, the timescales that you all are working on are very from minutes to hours to months and years. So for someone, and I asked this for the audience as well, what are the timescales that you're working on? We talked about planning this morning and you know, projections into the future versus what you're talking about. And so what timescales do you need the data on or the information?
Seasonal predictions are helpful. I attended a webinar earlier this year, which was kind of the summer drought outlook. That was helpful to kind of orient us to what we should be expecting. And fortunately, it hasn't been a very hot or dry summer. But in terms of making that power shutoff decision, within a week is typically the time scale. 5 to 7 days, you get that initial notification. We're expecting extreme winds, red flag conditions, things like that, because that is the time at which we need to start making plans. If we are going to de-energize, where and can we feed that power from a different place, minimize the size of that outage. We are also a co-op, so we're a member-owned nonprofit, which means we really owe it to our members to give them as much warning as possible. So having several days in advance, you can give a preliminary warning of, we're expecting these conditions. If they come to fruition, we may need to shut off power, to 1 or 2 days out where things are looking pretty certain, saying this is what we're going to do. So this is, your final notice, basically.
Yeah, right. So I'm really curious about this stuff. So it's, how common is these power shutoffs, or the fancy word you use? How often does that actually happen? And then is it usually accurate when it happens before? Like, how far out can you be accurate with it, I suppose?
It doesn't happen that often here in Colorado. It has happened with increasing frequency in California and Oregon as well. And they're getting some pushback on the accuracy piece of, okay, now you've de-energized a portion of line where after the fact we've realized you didn't need to, so you put people out of power for no reason. So they're kind of getting that from both ends, which is very difficult. It's, for us, it's a tool in our toolkit, is an absolute last resort. But in terms of how often it's accurate versus inaccurate, I think where it occurs in the West, in California especially, those conditions do arise, at least in terms of the wind that's forecasted. You can't predict which tree is going to break and where, or if one will, but you can have high probability that it's going to, and sometimes because if you don't do it, you're going to get killed. So yeah.
Hi, I'm Zamzam here from NREL. So my question is for you and then the rest of the panel about the data that is used to plan these power safety shutoffs. What kind of temporal accuracy or temporal resolution you have for this data? And would it help you to know that the high wind event is expected only during these few hours, or it is going to shift from this region to the other?
Yeah, I mean, as precise as we can get, both the time window in which that is going to happen and the region in which it's going to happen, the better for us, because we want to minimize the impact of having to do any power shutoff. So constraining it to the only area that's going to be impacted for only the time that's going to be impacted is that's the target we're trying to hit.
And then Eric, could you comment on the time resolution that you can provide from the models that you're creating?
Yeah. So the HER goes out to 48 hours right now. So 2-day forecast, and it's hourly output frequency. Obviously, we're going to be more accurate at closer ranges, and we see that quite a bit. As an event is kind of on the 48-hour horizon, we'll have quite a bit of run-to-run jumping around, but then we get closer to the event and we have more certainty. There's really a big move to go to formal ensemble systems that are trying to represent various sources of uncertainty in the meteorology, both in the initial conditions and in the actual physics, to be able to actually quantify the uncertainty at different forecast ranges of different phenomena. So we might be able to say, there's at a 2-day lead time, there's, a 30% chance of an extreme wind event, but then maybe at like a 6-hour lead time, we might have a higher confidence. So we think that having a quantification of the risk of something happening would be useful for this kind of decision.
So a question about forest management and models. So do you think that models could be useful to provide information almost on an operational basis for people in charge of forest management with the purpose of reducing the number of fires? So how can we translate what we learn from models, maybe operationally, so that the Forest Service or whoever is in charge can take the appropriate measures or actions to reduce the probability of fires starting?
So that's some of the motivation for the seasonal forecasting that I was doing. It can be used by a lot of different stakeholders, but that's one of the potential uses, is to be able to determine up to a 3-month lead time if the summer is going to be experiencing particularly severe drought conditions that are going to be very fire prone, and then mapping that on top of vegetation. They may be able to determine multiple months in advance how to do more proactive planning.
And then there are also existing models that can look at the structure and types of forest and look at like changing forest density and how that would impact fire behavior. And so using that in a modeling framework to then inform your management allows you to really identify where it's going to have the largest impact. And so that wouldn't be like the Earth system scale model. This would be more regional models that have, individual tree-based models.
So following up on the data and model outputs and desire, 2 questions primarily focused to the power, but how often do you look at updated forecasts? And how do you obtain this data? Is it something that you have people actively seeking every hour on the hour? Is it something you check once a day? Is it something you check 6 hours? Do you have a pipeline ingested and then it flags certain things?
Specifically for us, we subscribe to DTN Weather Services. They put out a daily 3-day risk forecast for wildfire specifically, but also wind gusts, thunderstorms, lightning, snow. Really, it's an energy event index, so it's specific to the power utility, any kind of weather conditions that could impact our ability to deliver power. Once a day, unless it changes. Like today, for instance, yesterday, I got a second one in the afternoon because they updated that. We are looking to invest in a more advanced platform that will update every 3 hours.
Thanks. From working with tribal communities and rural communities, the PSPS events can have a longer time frame. They're often at the end of the line. So if there's an outage, it may last for a couple days versus a few hours. And often these are vulnerable elderly populations. So it's not just about economic problems like the grocery store shuts down, so they lose all the freezer items. It's also about health considerations for folks that are on breathing machines or dialysis machines, and so people actually die from these outages, especially if they're prolonged. I was just wondering if any of you are looking at the PSPSs themselves as an environmental justice issue.
I could probably speak to that a bit because what you mentioned is a big part of our decision making, and it's something where it's a blind spot for us because we have our members self-report if they are on medical devices and do not shut offs, and sometimes they don't report. So a way to address that, particularly with end-of-line customers in the rural areas, is having a generator rebate program. It's something that we've been talking about where members can obtain a generator because it's not just preemptively shutting off power. We also implement more sensitive settings on red flag days and things, so outages are more likely. And similar issues, it takes a while to get back online. So for those reasons, it's something we've been talking about internally of reimbursing our members, particularly the insecure ones, for generators so they can have that power.
Hi, I'm Evan from Texas A&M University, Corpus Christi, and I was interested in, not just if there is interest in not just forecasting, predicting the wildfires themselves, but wildfires that develop into a pyrocumulonimbus event, because that can dramatically change the impact of like 2 wildfires with the same general characteristics, but one developing into the pyro-CB. Now you've got like dry thunder in the mix, and you already have like a fuel scenario, right? Like a high wildfire scenario. Now you're putting dry thunder in there, smoke plumes, etc. I'm just wondering if there's any like interest in or research into predicting that aspect.
Yeah, there's definitely a lot of interest in that. I know the Naval Research Lab has some experimental forecasting capabilities and detection. They have a long database of pyro-Q and pyro-CB events. In terms of the numerical weather prediction, we're not able to do that yet, but it's definitely something we're interested in. We want to start to move to higher resolution, probably not for our like CONUS scale numerical weather prediction models, but these smaller nests that could be deployed if there's going to be a wildfire outbreak or something. And we want to experiment with putting heat and moisture fluxes in to start with, just heat and moisture fluxes at the surface where there's a big fire, and just to see if we can get some response. Because these models at high resolution, they are convection allowing, so we ought to be able to get fire-induced thunderstorms. But that's definitely an active area of research.
Okay, thanks. Yeah, I was asking because I was doing an internship with NRL on that research. So it's just
Nice,
curious how interested the community is in that. So thank you.
Well, and I can let you know that NASA had a call with NOAA recently talking about, so Dave Peterson is the one who's doing this work. And so he's been collaborating with NOAA. And so NOAA and NASA are talking about like a partnership to sort of explore this with Dave Peterson, who's at the Naval Research Laboratory.
So we mentioned about, I think Eric, you mentioned that we had 12-hour lead time on the Marshall Fire, that we knew that the winds were going to be pretty strong. I'm assuming that that happened after the fact, and we didn't know that ahead of time. So I guess my first question is like, what other markers should we be looking at? I mean, we talked about vegetation stress as it comes to dryness, but basically as we're building this probability statistic, what other things need to be considered so that the power company has that ability to say, okay, the risk is pretty high, we need to divert it or de-energize, I think is the word that you guys used, to do that, because I guess the concern is if we have the same situation happen again, do we have that communication mechanism so that we can react properly, so that we can avoid something like the Marshall Fire?
Yeah, I think for that case, there wasn't really a lot of attention on the fire danger before the event, partially because of the season and the focus. Actually, there was, so I mentioned the 12-hour lead time because the longer range forecasts were not necessarily indicating the high winds to really come all the way down to the front range urban areas. But our forecasts were key for the National Weather Service to be able to issue the high wind warning, in the middle of the night, that night before the event. We are interested in trying to quantify like fire weather in kind of a more formal way. So we've been working on this new product that we're calling this hourly wildfire potential to try to get away from these once a day type of fire weather indices to be able to quantify the effect of meteorology on a sub-daily time scale. So we've seen a lot of examples in recent years of fires dramatically changing their behavior based on the meteorology due to like an outflow boundary or even changing fuel loads that they encounter. And so we want to develop a new index that's maybe more tailored for hourly quantification of the wildfire risk. So I'm not sure if I answered your question fully, but
the other question is like, so it sounds like we don't have the metrics ready yet for basically like a power utility company would have to have actionable data, right? When this happens, I shut down, or I do something. So it sounds like we're not there yet. So we basically have the same vulnerability that we had back in the Marshall Fire, that we might know all these conditions that are kind of aligning and potentially creating this very risky situation. But that's the first part, it sounds like that's not ready. But then the second part is like, do we have those communication mechanisms so that we can, other than like the high wind alert, so that we can say, hey, public utility, you need to take a look at this and potentially take action as necessary. So I don't know, maybe that's a question for someone else in the panel.
I'll just say one thing. There is the red flag warnings that have been mentioned already that the Weather Service issues. On the Marshall Fire Day, there was not a red flag warning in effect because the relative humidity was not expected to quite reach the criteria for issuing that. So there is discussion about whether the kind of the framework of the red flag warning needs to be revised to do a better job. Yeah, maybe that's all I'll say.
Yeah, and a piece of that tool speaks to your question and also yours, because we can't be monitoring this all day, every day. There needs to be an automated alerting process built in to where when certain thresholds are reached, that is sent out, if not to utilities that you're connected with, to your researchers who can then make contacts in the utility to say exactly that. This is something that you should be paying attention to, especially for like rapidly developing conditions like Marshall.
I'm going to go. Sorry, Brad. Lilly, I wanted to just ask you for a little bit more details on your project. It's really exciting to hear about a successful academic private sector collaboration. So what kind of products do you give to SCE at the end or during the project? What kind of interactions are there, and what are they going to use with the information that and the model that you provide? Oh.
They have an existing process right now. They use ArcGIS and Landsat data and their own little kind of internal model that they've developed to predict where they should send their vegetation removal crews. And they want to improve on that. It's not really great. It's the temporal scale is about 1 year. And so some of the things that we're doing, this project is still really in early stages, but some of the things in the last several months that we've come across, we have had a lot of meetings and we're kind of co-collaborating to produce this. And that's been really important, is learning how to, I think somebody mentioned industry speak and academic speak, learning to speak each other's language, understanding the stakeholders' needs was very important. And, and then conveying to them what some of the limitations of the science could be, and some of the limitations of the modeling. And so where we're at right now is they want to continue to use ArcGIS. So we're going to make a plugin that is interoperable with ArcGIS. We have a lot of remote sensing expertise on our team. And so we're coming at it from a remote sensing perspective. And we're going to use an algorithm called MESMA, which is a spectral unmixing algorithm and we're using ESA Sentinel-2 data. And so we're going to look at the sub-pixel scale or pixel by pixel and look at the mixture of spectral signatures from different vegetation types, not only the different vegetation types, but their life cycle. And so it's going to be a bit of a complicated problem. And like I said, we're working on it. The first kind of problem that we ran into was that the MESMA algorithm has to be updated. It hasn't been maintained for the last, few years. So we're updating that. It's one of Earth Lab's missions is to make sure that anything that we produce is open source. And so while there's going to be the proprietary aspect for SCE, we also want to make sure that we produce something for the community that can be used, for the academic science community that can also be used. So. And also for the utilities, absolutely. Absolutely.
I have a question for you, Lily.
Yes.
Is that just underlying environmental conditions that they layer their assets over, or is there any consideration to the age and health of their infrastructure?
They have actually invested a lot into different types of research, and we have what we're calling it the 3-pillar model. So there's an atmospheric climate component. There's another component. They have an incredibly robust model of their infrastructure, which they developed in-house. With the data, their data science team. And then the portion that we're working on is the vegetation. How do we predict? And I should have included a slide for this. There's the brown down, there's a green up of vegetation, and then there's brown down. How do we capture that moment where brown down is occurring? And that's what they want to do, but they want to do it 3 months predictive, which anyone who's tried that knows that's really non-trivial. And so, yeah, that's the component that we're working on.
So I'm going to try and make a question that tries to put some things together. It was great to hear that there'll be wharf smoke potentially ensembles, but those are massively expensive undertakings. It's great to hear that there's machine learning tools that can give you kind of S2S kind of predictability. One question is, are we at the point where we can, and we've got, refined vegetation characteristics so we really get at fuel moisture and those kind of things. Are we at the point where we could generate a synthetic data set that could be used, that was tied to actual fires, that could be used to begin to develop either predicting fire probability or predicting fire, time of arrival, that kind of issue that was addressed earlier? How far away are we from being able to do that, to trust the predictions enough to actually use them as training data.
Yeah, that's a great question. One that I've been thinking about is, so on the slides I showed about the, let's say 4-kilometer drought index prediction at a seasonal time scale, because there's strong relationships between flammability and fire, that can be used to make a prediction of potential probability. But the large uncertainty in the room is whether an ignition will occur in that 4-kilometer pixel or adjacent to that 4-kilometer pixel, which is very difficult to know 3 months in advance. So we can make a prediction of, let's say, fire hazard at a seasonal time scale, but whether that pixel will actually, or a 4-kilometer grid box somewhere in the US will catch on fire or not, is very difficult to predict, because even if it's very fire prone, ignitions can be quite random.
But we do have, I mean, the utilities are concerned about ignition along their transmission lines. So there are regions that are definitely being focused on, and it might help with the, decide, so that the California utility is thinking, it's using some model to say, what part of the line do we need to treat? Maybe if that could be further enhanced, then you potentially avoid these, these power shutoffs. I don't know.
Yeah, that's a great point. So if I have, I don't know if this data is out there and able to be shared, but if I had a map of where all of these electric lines are and could overlay that onto my drought prediction, I could provide information about fire hazard along those lines at the S2S scale. I haven't seen that data publicly available though on a continental scale, but maybe it is. I would love for it to be.
Yeah, for Bonneville Power Administration, it's publicly available data on Esri.
Great, thank you.
Okay, sorry. Here, there's a bunch of hands that shot up after that.
All transmission lines in the U.S., the locations of them are available on ArcGIS provided by the Department of Homeland Security. So every transmission line above 69 kV is available.
That's wonderful. Yeah, I'll look into that now that we're making the next step in our forecasting.
Yeah, that's great.
That's awesome.
Yeah.
Just to follow up on that, some of our transmission system is 44 kV, so it wouldn't be on that database, as well as our distribution system. We have 300 miles of transmission, 5,000 miles of distribution, all equally capable of igniting a fire. So it's not so much, one voltage versus another. For me, the component, this is why I asked Lilly, is having really robust knowledge of your own asset health, and also your outage data. You can begin to assign probability and likelihood of failure to your assets and overlay that with the underlying risk. So you have both conditional risk and consequence risk.
Thank you. Can I ask a quick question while I'm walking up there? Could you explain just the difference between transmission and distribution lines?
Sure. Well, it kind of varies utility to utility how they want to define it. But the transmission system is for longer distance, so you up the voltage a lot higher, and sort of depends on your infrastructure and how far you need to go. The highest we go is 115. Curtis, I'm sure you're 200 and above. Yeah. Distribution is more on the scale of 12.5 kilovolts. And that gets stepped down at the transformer to 120, 240.
Thank you.
Hi, Jason Odkin, University of Wisconsin-Madison. This is a question for Jordan, Lilly, and other people from utility and distribution companies. I'm always curious how people are using probabilistic forecasts, because they're going to give you the most, we hope the most reasonable estimate of whether or not something's going to happen. But in the end, you still have to make that a deterministic decision based on that probabilistic forecast. So like if we were to I don't know, like, Eric runs this model, says that there's, an 80% chance that we're going to have, really bad conditions. You then decide we're going to shut down the power lines. But if that forecast is reliable, that means that 1 in 5 times you don't need to. How do you message that then? How do you actually get the point across to, to customers, other people within your businesses that actually that was the right decision to shut it down, but sometimes it's going to look like we're wrong.
Yeah, that's the difficult position. But the short answer is better safe than sorry. But the other part of it that goes into, there's some really sophisticated fire simulation modeling that can tell you if a fire starts here, it could have this consequence, this number of structures burned, et cetera. And that's a piece of the technology that we're investing in. So that plays into it as well. Is it, a high probability of a fire or of conditions that could start a fire in an area where there's high consequence if that fire starts? That plays into it as well, because if it's, in the wildland and confidence is not so high, we probably won't shut off the power. If we do start a fire, that would be bad, but it wouldn't be as bad as if we did it in, downtown Conifer or something like that.
Before you jump to the next one, just along those lines, there's a ton of research on communicating risk. It's going on in the weather community. In fact, there's experts here at NCAR that work on that. And I wonder if there's a lot of ways that the utilities in their communications could take advantage of that research. And it might be worthwhile bringing in some of that into the next conversations.
So yeah, my colleague behind me said social science. I want to make sure we get that point. So to what degree is it purely just education, right? So like if I told a person in California, you have to limit your shower or water use because of blah, 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 they would quickly understand. So in this case, if I said I had to shut your power off, I don't think anyone would understand. So like, how much is that just on us? So like when we predict the rain, people understand that 25% or 40%, 50%, it's still an issue with people fully getting what that means, but they do get it. It's not 100% like in your area, blah, blah, blah. It's still iffy, right? So how much is that on the social aspects, and what have you seen done so far? To any of you, maybe? I don't know. I haven't seen much, but if y'all have seen anything, I'd like to know, or ideas.
In terms of the education piece, it's definitely a big component, and there are a lot of community advocates in our territory that do great work, but I think we as a utility bear some responsibility for that as well. Not just with the power shutoff piece, but also individual home hardening and mitigations and things like that. But specifically for the power shutoff, with the fire in Maui and the Marshall Fire and the fires in California, it's being so widely publicized that is sort of taking a lot of that off our shoulders. People do understand and are asking us now, what are your plans for doing that? So I think just by ingesting what's going on elsewhere, they're coming around to that understanding that may become necessary.
I'd just like to add one more little layer to this conversation about shutoffs and how we may or may not respond. So Tri-State, we're generation and transmission. We do not do distribution, so we don't bring power to your home. We rely on a local co-op to do that work. So for us, if we're making a decision on a high risk day, a high likelihood for an event day, and try to decide whether or not we're going to turn off power, we have to consider all those communities that are down the line, that could be hundreds of miles down the line, who don't have the same activity, don't have the same level of risk in their neighborhood. And then we would be working with a co-op that would ultimately, or many co-ops, that would lose that power. So it's a very nuanced conversation, and you know, these are not things that are widely understood. I don't think. I didn't know them till I came to the industry. I'll tell you that. So it is a challenging conversation, but I think, like Jordan said, the Mauis, the Marshall, and unfortunately whatever happens next is gonna feed into that conversation and help people better understand, you know, what those limitations are and what those trade-offs may be and the justifications that we may have to provide. But that's where your data, right? That's where your data really help us provide that justification. You know, if we can say with some degree of certainty with the best data available that we're going to experience an event, that is a tool to communicate to people. It's not we're just saying, well, we just put our finger up in the air and it looks like a high fire day, we're going to shut the power off. Now, we got some pretty significant science behind these decision makings, and that's where I think you guys play a very critical role in that.
Yeah, and to your point, it's maybe a little easier for a distribution co-op to make that decision because it's all very localized. More difficult to explain to somebody there's a PSPS event 100 miles away on the transmission system, and that's why we can't serve our load, even though it's not a high-risk day here.
I was going to follow on to that type of conversation, which is maybe as scientists, we could help supply that information to where you could, I don't know how difficult it is to make a break at a different spot to say, this is a fire-prone region that we've known year in, year out, that's very susceptible to issues. So maybe you can put mitigation factors already in to where it doesn't have to go 100 miles in this particular area. So you could spend your resources there. If that's something that's useful, maybe we could learn from you folks what you need in that regard. And we could do our fancy model stuff and say, this is the area, this is your proof. You know, this is historically 10 years, 30 years. This is how much we expect this area to be impacted. Maybe that's something of use. I don't know.
I kind of add to that. To me, this is situational awareness question. So we're thinking about this for kind of the national fire management, where, you know, we will have this alert dashboard that will allow the different fire regions to decide where they need to be deploying. This is like on a kind of daily kind of basis. Where do we need assets? And there's lots of different kind of segmented power, regions. I don't know how much there is a national kind of, there's a national grid. How much is there exchange among those power regions? And can we move to a point where we have predictability like we do now in the last decade for hurricanes, where again, emergency management pre-deploys because they have enough confidence that this is where, starting with a 3-month forecast, this is where we need assets. Is there a possibility we could move to that kind of pre-deployment, do everything you can to mitigate the risk, but then also know where with the fire agencies, where you should be anticipating deploying?
Yeah, well, so there's one of the issues with fires now is that we're having more fires happening more frequently at the same time. And so each of the regions that have the resources, even if you give them a 3-month forecast, that 3-month forecast gives them the capacity to say, let's do some staging in advance. But then it's up to those regions as to whether or not they want to release those resources to another area. And so if another area has a fire and they're saying, look, I have a strong need, they can say, well, our forecast says that we might also have a strong need. And so there is not, it's the risk is preventing us from providing those assets in a more strategic fashion. And so there needs to be more coordination, and exactly where that happens, I don't have a recommendation there, but it's identified as an area that needs improvement. And so even though like Ronnie's model can provide this forecast 3 months in advance, it's like when you get to that week out or 2 weeks out, people want to hold on to their resources to protect their communities.
Yeah. Can you hear me? Yeah. So my question is about the predictability in a scale of hours. So if we're talking about a fire that has already ignited, is there any use to have an actual fire behavior, like a rate of spread or a direction of propagation? Or is it too like last minute
for the utilities to actually do anything.
No, that would be helpful. The pace at which these fires can move would allow us to know if we need to de-energize ahead of the fire, or even do tactical vegetation management, like get our tree crews out there and cut fuel breaks ahead of our critical infrastructure. So even hours is enough time to know, okay, things are moving in this direction. Let's get our crews here and start cutting line.
Thank you. We're coming up on time. Are there any final questions? Oh. Yeah.
I had a comment from the interconnection perspective. As reliability coordinator for most of the Western United States, we get PSP reports from Edison, PG&E, other people, and they usually give us a list of lines that are threatened, and we'll start studying those lines out of service as we move into the event. And what we'll do is we'll balance that against scheduled equipment outages. So if we see, oh, this line is 230 line is going to be out in the Bay Area in San Francisco, but we have another competing facility that is out for maintenance, we may call for that to become back in service at a time to prepare for that kind of event. So over the years that we've had this PSPS evolution, and believe me, the first time we had a PSPS event in Northern California, I was a very unpopular person with my Sunday morning golf league, but they just didn't understand it. So it sort of went into an explanation. Over time, PG&E and other companies have gotten better at it. They've isolated their facilities that are prone, and they've done inspections, hardened their facilities, done tree management, those type of things to reduce that list. So it's really been an evolution going forward. And we've seen PSPS programs or like expanded to other areas of our region now as well. So it's growing as well.
Thank you. And we'll wrap up this session. I really appreciate the conversations, the excellent panelists here. So let's thank them, please. And honestly, Tim did a lot of work to put this panel together. So I do want to acknowledge him too.
Thanks.
I didn't